This is problem 48 from the magnetic force. The long straight wire at right carries current I. The rectangular loop carries current 2I, has edge lengths A and 2A, that means one block, has a width A, and lies a distance A from the straight wire. Find the force acting on each side of the loop and the net force on the loop. So first, let's label our sides. So we'll call this 1, 2, 3, and 4. Sides 2 and 4 will be easy to do. In this section, we saw how to calculate the magnetic force acting on a straight wire in a uniform magnetic field using IL crossed with B. We can do this for side 2 and for side 4 because the magnetic field is created from this wire here, and the strength of the magnetic field, if you're staying the same distance away from this wire, is constant. But if you change the radius, then the strength of the magnetic field changes. So if you're going on side 1 or side 3, then the strength of the magnetic field is changing as you go from one end of the wire to the other. But for 2 and 4, as you go along the length of each side, the length of 2 and along the length of 4, B is not changing because B, in this case, is coming from this wire here. And so if you're staying the same distance away, it's not changing. And if the current's going in this direction, then where the loop is, your fingers are going into the page. So that is pointing in the negative k-hat direction. Okay, so in the past when we looked at calculating the magnetic field, calculating the magnetic force acting on a wire, it was a uniform magnetic field, but now it's not. Now the magnetic field is changing as you move away. Okay, so we have, for side 2, the current in this wire is 2I. The length of this side, side 2, is 2A. The current's going in the I-hat direction, so L is equal to 2A I-hat. That's crossed with B, and B is the magnetic field created by the straight long wire here, and that's mu naught I divided by 2 pi. And here we are distance A away, so R is equal to A, and it's pointing in the negative k-hat direction. I-hat crossed with k-hat is negative j-hat, but it's a negative k-hat, so I-hat crossed with negative k-hat is positive j-hat. So this is, I can cancel that 2A and that, so that's 2 mu naught I squared divided by pi in the j-hat direction. Side 4 is going to be similar. So you have the current in side 4, which is 2I. The length of side 4 is 2A. The current's going in the negative I-hat direction. Cross that with mu naught I divided by 2 pi. Now R, if you're on side 4, that's 2A away from the wire that is creating the field. So that's divided by 2A, but still in the negative k-hat direction. So now we have this 2A cancels with that 2A. You can cancel this 2 and that 2. Now I have negative I-hat crossed with negative k-hat, or you can just do I-hat crossed with k-hat, which is negative j-hat, and a negative times a negative is a positive, so it's in the negative j-hat direction. And we have an I and a mu naught, so that's mu naught I squared divided by pi j-hat. Okay, now For sides 3 and 4, we have to use the equation that is on page 4. The force is equal to I ds crossed with B. Actually, maybe it would have been fun to use this equation for side 2 and 4. And if we did that, we would integrate from one end of the side 2 to the other end of side 2. The I is constant that can come outside. The B, the magnetic field on this side, is not changing, so that's why we didn't need to use this formula. And so when we integrate from one side to the other, ds, as you go from 0 to 2a, that would just give us the 2a that we got there, and at that point this equation would just become what we had up there. So now let's see how it works when we look at side 1. So the current in side 1 is equal to 2I, and ds has a magnitude, ds. The direction is given by the direction that the current is going in, which on side 1 is in the j hat direction. And B is still equal to mu naught I divided by 2 pi r, and that is in the negative k hat direction. I have an r in my equation here. They don't give me steps like they did for the integral in the magnetic field, but if I choose a differential element here, r is going, because this is the distance from the wire here, so this is r, but that's going to change as you go from one end of side 1 to the other. So I really shouldn't call this r, because it depends on where I am on side 1. I'm integrating with respect to s. If I just call this distance s, that makes it easy. So you could choose s to be equal to 0 somewhere else, but that's I think the best or the easiest choice to make here. We have to do the cross product, so we have j hat crossed with negative k hat, or I'm just going to say j hat crossed with k hat is I hat, but then you still have the negative sign here. So, and if we say s is equal to 0 here, then we're integrating from a to 2a. So if you chose s to be equal to 0 somewhere else, that would change your limits of integration, but you would still get the same thing after integrating. Let's pull out everything we can, which would be a 2 mu naught I squared divided by a 2 pi, and the 2's cancel out. We have a negative sign, and we said j hat crossed with k hat was I hat. So we have an I hat also. This is from a to 2a. We have our ds here. I think I pulled out everything except for the s in the denominator, and this is in the I hat direction. Well, we know how to do this integral. This is just the natural log. So if I plug in my limits of integration, that's the natural log of 2a minus the natural log of a. But when you subtract natural logs, you could divide them instead. So that's just the natural log of 2 in the I hat direction. Fortunately, side 3 is going to be very similar. What changes on side 3 is just the direction that the current is going in. And the direction that the current is going in tells us the direction of ds. So now that's going to be in the negative j hat direction. So really, that's the only difference, is the sign. So we have I, which is still I. No, it's 2I. It was 2I before though, so that doesn't change. So that's the current inside 3. The magnitude of ds is still ds, but now it's going in the negative j hat direction, crossed with the magnetic field, let's say here, which is mu naught I divided by 2 pi s. That's going in the negative k hat direction. j hat crossed with k hat is I hat, and we have a negative sign and a negative sign. So that's 2I squared u naught divided by 2 pi, and the 2's cancel. We're integrating from a to 2a. I have a ds divided by s. That's in the I hat direction. After integrating, I get mu naught I squared divided by pi natural log of 2 in the I hat direction. We found the force acting on each side. Let's just write everything nicely below. So the force on side 1 is equal to negative mu naught I squared over pi ln of 2 I hat. The force on side 2 is equal to what we have here, 2 mu naught I squared over pi in the j hat direction. The force on side 3 is equal to mu naught I squared over pi ln of 2 I hat, and the force on side 4, that's what I have up here, negative mu naught I squared over pi j hat. So we have there the force on each side, and we want to find the net force. Watch this. Side 1 and side 3 added together give us 0. When I add the force on side 2 to the force on side 4, I do not get 0. So in this case, we have a closed loop, but the magnetic force is not 0 because the field is not uniform. So for the net force on a closed loop to be 0, it would have to be in a uniform magnetic field. In this case, the field isn't uniform because it depends on how far away you are from this current carrying wire. So when I add all this together, 1 and 3 cancel out, and if I do 2 plus 4, that's 2 mu naught I squared over pi minus mu naught I squared over pi, which is mu naught I squared over pi, and that is in the j hat direction. Before we leave this problem, let's just check to make sure that we got the right direction on each side by using the right-hand rule. So if the current in the wire is going this way, we said the field is going in the negative k hat direction. So I can do the direction of the current crossed with the direction of the magnetic field to give me the direction of the magnetic force. So let's start with side 1. So the current's going this way, the magnetic field's going into the page, so the force should be going in the negative I hat direction, and we found that it was going in the negative I hat direction. So that's good. For side 2, the current's going this way, the field is going into the page, so the force should be going in the j hat direction, and it is. For side 3, the current's going this way, the magnetic field's going this way, so the force should be going in the I hat direction, and it is. For side 4, the current's going this way, magnetic field's going into the page, so the force should be going in the negative j hat direction, and it is. So that concludes problem 48.